I know some of you have maybe seen one of my collaborators give this talk or seen me give this talk in Nottingham a few weeks ago, but hopefully I can share a little bit about our work. And this is all joint work with Kenny Asher, Yu-Chen Liu, and Jiawei Wang, and several of them are in the audience. So please feel free to ask questions, and let me tell you a little bit about what we were able to do. So this story is about the moduli space of curves. So let MG be the moduli stack of smooth genus G curves, where the genus is at least 2, and MG bar be its natural compactification. Be the stack of Deligne-Mumford stable curves. So I'm sure most of us in the audience are aware, but just a stable curve C is at worst nodes as singularities, and the canonical divisor of C is ample. So there's several equivalent definitions, but this is one. You can, if you're not a stack person, think about the moduli space as I'm talking, and there will be not much lost. This talk is about sort of questions about what other compactifications of MG are there, or what other, maybe not all of MG, but what other compactifications can we make if we start with some open subset of smooth genus G curves, but phrased in maybe a precise way. So one observation about MG bar is what we add to compactify. So the notation delta is usually, we'll write it as delta 0, delta 1, delta G over 2. Let this be the boundary divisor on MG bar. And if you haven't seen this notation before, delta 0, I guess generically, parameterizes irreducible curves with a node. And then delta I, for I greater than 0, oops, again, at least generically, parameterizes curves of the form where I guess whose normalization at that point is disconnected, and one of these components has genus I, and one of these components has genus G minus I. So the boundary divisor of MG bar has this natural decomposition. This can be written as the sum of these other boundary divisors, and we know quite a bit about the geometry. So in particular, the I don't know, kind of salient facts about this that I want to use are the canonical divisor plus this delta is an ample divisor on the stack. If you don't want to think about divisors on a stack, there's a suitable version of this for the moduli space. You just have to be a little bit careful with what you put for delta 1. But in any case, this is ample. And part 2, the actual moduli space itself, so let's say MG bar delta. So this is the coarse moduli space. And this is the boundary divisor. We'll use a capital delta for the moduli, or the boundary divisor on the space, has mild singularities. And what this means, in fact, is that the moduli space MG bar as a projective variety is a minimal model, or a log canonical model, to be more precise. So what this tells us is that MG bar is some sort of log canonical model that we can construct as the projectivization of the canonical ring, or the log canonical ring. I guess this should be the stack. Oops, put my sum already. So, I'll say. So this is one way to interpret MG bar. MG bar itself is a projective variety. It has this modular interpretation as a stack or a moduli space parameterizing stable curves, but it itself is lives in the broader context of the minimal model program. And a question you could ask, which is maybe the motivating question for where many of this begins, if the genus is sufficiently large, mg bar is of general type, and we might ask, once you're in the framework of the minimal model program, if you have a variety of general type, you could ask what its canonical model is. So the question is, what is mg bar can? The canonical model of mg, which is essentially this canonical ring with no delta. This question I am not going to purport to answer whatsoever in this talk. This is, I think, a very difficult question. Even just the question of what curves in mg, like they correspond to a point of mg bar, which of those curves should persist to be points of this space? This is a very hard question, and I'm not going to try to answer this, but if you did want to answer that question, one way you could imagine doing that is considering this space, where you have a delta, and this space, which is proj of the associated ring without a delta, and try to interpolate between them by sequentially diminishing the coefficient of delta. So we could ask a second question. For any alpha in 0, 1, we'll say intersect Q, so I don't have to worry about R divisors here, such that K mg bar plus alpha delta is big, what is what I will call mg of alpha, which I will define to be proj of, again, the associated canonical ring, where I'm taking alpha delta instead of delta. And this is a little bit of a coarse question when I just say what is. This has many interpretations. The interpretation could be, what variety is this? Forget any sort of modular meaning of it. mg is a projective variety, and this is some minimal model, or some sequence of minimal model extremal operations. What is this as a projective variety? But maybe I want to be a little bit more precise and say, does this have a modular interpretation? And this question, if you could answer this for every alpha, and you decreased alpha from 0 to 1, would ultimately get you to an answer to this question. So this is all the motivation for this story. I am going to mostly focus on this question in genus 4, as is said in the title. And in genus 4, we are not in the general type case, so we won't be able to go all the way to 0, but we will be able to say something interesting. So this is the setup, and these kind of questions are collectively referred to, among other things, but as this Hassett-Keel program. So the subject in the title is, what happens when I run the minimal model program on mg bar, and can I interpret for each alpha such that this kx plus alpha delta is big? What can I say about a modular interpretation of this space? And quite a bit is known. So I think the first things that I will review is a little bit of the history, which we can talk about for any genus, not just genus 4. So history / what is known. So most of this started with a paper of Brendan Hassett in genus 2, but one can maybe take a step back. Instead of just asking about this minimal model program, we know starting off that kx plus delta is ample for any g. And you could just ask, as you start decreasing alpha, when do you hit the boundary of the ample cone? When is this no longer an ample divisor? And that, sort of by definition of this canonical ring, will be the first place that something changes. So what is known by study of various things? For any genus, say for alpha greater than 9/11, this divisor is ample. So this is, I guess, in Hassett's paper, and maybe follows some work of Kornalba and Harris on the ample cone of mg bar. And what that says is that mg bar alpha is just mg in this case. But at 9/11, something happens. There is a contraction. So there's a morphism from mg bar, let's say 9/11 plus epsilon, to whatever small epsilon you want, to mg bar 9/11. And this is a non-trivial morphism that is, in fact, a divisorial contraction. Here's the eraser. And this contraction, back to the sort of refinement of question 2, does this have a modular interpretation? This has a modular meaning. I'm just erasing delta I. This divisorial contraction is the contraction of delta 1. So let me write that. And then we'll review the first few steps that are known before getting into the genus 4 case. Pardon? For this genus 2 is OK. You still have a contraction, one divisorial contraction in genus 2. Yeah, this is the only step in genus 2. But yes. So you have a divisorial contraction, and what does it do? This contracts the locus of curves with elliptic tails, which elliptic tails means you have some genus 1 component, an elliptic tail, glued to a genus G-1 component. And this is sort of unsatisfactory to say it contracts this locus. That's what it does. But in fact, mg bar at 9/11 has a modular meaning. This is, in fact, a moduli space constructed by Schubert of pseudo-stable curves. And what is a pseudo-stable curve? It is a curve where the canonical divisor is ample, you have at worst cusps, and you have no elliptic tails. So you've traded the information you get with this genus 1 tail hanging off for a cusp. And this was constructed as a different moduli space. And so it turns out that this morphism is a 1, birational operation in the MMP, but 2, has a modular meaning. We can explain what's going on the level of the universal family, in fact. So that's the first step. And then there are several more steps that we know. We know the first few steps of the minimal model program in arbitrary genus, and then we get to a point where things are unknown. So we're doing time. Review that before getting into the new inputs. So there will be a change, but for all genus at least 2, we have the next critical value of alpha is 7/10. But something different does happen for genus 2. At genus 2, this is just the end. When g equals 2, this moduli space 7/10 is just a point. This divisor is trivial. This kx plus alpha delta is trivial, so moduli space goes away. But for g greater than 2, this is what is known as the first flip. So let me write this out, and then I'll add some references. So the first flip, you have a map from this mg bar 7/10 plus epsilon is a rational map to mg bar 7/10 minus epsilon, and some base of the flip at mg bar 7/10. And again, this has, this birational map has a modular meaning. So what's going on here on the left-hand side, you have what are called elliptic bridges. So you have an elliptic curve connecting genus 1. So the middle component is genus 1. It's connecting two other parts of the curve. That's your elliptic bridge. And it is getting interchanged on the other side of the flip with a tack node, which locally is in the form x squared equals y to the 4th. So this has, again, a modular interpretation, genus 1. And these were studied in several cases. So this, the genus 2 case was worked out by Hassett. And the first flip was worked out in some cases, or some partial results in work of Hyun and Lee, and then in generality by Hassett and Hyun, and constructs this as a flip. I'm hiding a lot because I'm not telling you how any of this is done. That's what we're going to I'm going to discuss a general framework for how you might prove something like this, the existence of a diagram, and how you could guess what's getting interchanged and so on in a moment. So if you're waiting for how did they do any of this, I will give you a way to think about proving these steps. Oh, thank you, Lena. G, strictly greater than 2. Yes. And then the next step is going to be the last bit of history that we know we know the next step of the Hassett-Keel program. Is there, okay, yeah, okay. I'm not telling you quite a bit what's happening here. The elliptic bridges are over here, and the tack nodes are happening here, but this also has a modular interpretation. But that's where we're going to get into the world of stacks to know what the closed points of this should be. So we'll get there in a second. And then, again, something happens when genus is 3. We know, so the next step is some random rational number, 17 over 28, where the hyperelliptic divisor, we'll call H3, is contracted, and then at alpha equals 5/9, you get a point. So for small genus, there are differences in the Hassett-Keel program just because some of these steps, right, like this just purely can't appear in genus 2 because you don't have curves with elliptic bridges in genus 2. So you have some small genus differences. But for genus 3, this is all worked out. And this is, there's several different interpretations. One interpretation in this Hassett-Keel setup is by work of Hyun and Lee. And then the next thing that we know for any genus is the next critical value is 2/3, and you have a second flip. And so you have the same diagram that I wrote over there, mg 2/3 plus epsilon to mg 2/3 minus epsilon, mapping to mg 2/3, the base of the flip here. And this has a similar interpretation to all of the contractions we've seen so far. So the first contraction is the contraction of elliptic tails. The second thing is you can imagine on the level of the family of curves, contracting this elliptic bridge to produce the tack node. Here we have something similar. You have the contraction of, genus 2 Weierstrass tails, which means that one of these curves has genus 2. And the point that it is connected at is a Weierstrass point of the genus 2 curve. And these get interchanged in this flip with what are in several contexts are called Ramfoid cusps, which are a higher order cusp. So something that looks like x squared equals y to the 5th. And this second flip is work of Alper, Fedorchuk, and Smythe, building on some work of those three authors, also with van der Weyck. So this is the state of the art. For any genus, this is as far as we can go. And there are many conjectures. So the paper of Alper, Fedorchuk, and Smythe give many conjectures on what should happen next for various genus. And maybe to indicate what, if you are not familiar with this and you look at this, you might think that, oh, okay, well, look what's happening. We see a pattern here. We had cusps, x squared equals y cubed. And then we had tack nodes, x squared equals y to the 4th. And then we have x squared equals y to the 5th. Maybe we see a pattern emerging. Some of the subtlety is this is a coincidence of small alpha, or large alpha. As alpha starts to increase, there are actually loci that parameterize smooth curves that are going to have to get modified in this program. So the first unknown case of genus 4, what happens after 2/3 minus epsilon, we know that at some point the entire divisor, or excuse me, it's not a divisor, the entire locus parameterizing hyperelliptic genus 4 curves will have to get modified by this program. This kx plus alpha delta is not ample on that locus for some sufficiently small alpha. So you can't just naively follow this pattern and be like, next, x squared plus y to the 7th, or 6, next, x squared plus y to the 7th. There's some subtlety. So in most of my talk, I would like to sort of explain what happens in genus 4 and the general framework, which is in somewhat generality, started in this work of Alper, Fedorchuk, and Smythe, of how you would approach these kind of problems. I guess that concludes my history portion of the talk. There's also a lot of interesting questions here, right, that are related to just the ample cone, the Neff cone, the pseudo-effective cone of mg bar. I will also not purport to discuss any of those things, but so before I get into what we prove and how we prove it, I want to introduce sort of a general method or an idea behind how these wall crossings, how these birational contractions and flips are constructed. So a method to prove the modularity. And modularity, I don't really mean anything precise by this. There are, if you look in the works of Alper, Fedorchuk, and Smythe, some precisely posed modularity conjectures. In this, I just want to say a method to prove, but if you identify a birational contraction, how can you identify these things as a moduli space of curves? And this is, again, highly motivated by the work of Alper, Fedorchuk, and Smythe. And the idea is to use the theory of stacks and guess, as many things in math, guess what you think the answer should be and then prove that that's the answer. So one method is to construct a stack, like hopefully a nice stack, but I'm not going to put adjectives on this yet. Mg alpha, I guess I should decorate this. Let's put a double line here. Mg bar alpha, that parameterizes the curves conjectured to be, quote, stable for this value of alpha. And this is the part where I mean you kind of guess. So I haven't defined stability, but let's just say stable at the moment means the curves that should appear in mg bar alpha. You make an educated guess on what these curves should parameterize. And there are several ways to do this. One way to do this, at least when alpha is very large, are to use explicit descriptions of, like, say, the ample cone. For example, this, it's gone now. Oh, this locus of elliptic tails, one can actually prove that the, as you decrease alpha to 9/11, at 9/11, you hit the boundary of the ample cone, and families of curves with elliptic tails are exactly what are trivial on that divisor. So you can do computations using the ample cone. But you can also do computations. What Albert Fedorchik and Smythe sort of proposed was using the idea of the stack. So I won't say too much about this. If people want, they can ask more. But roughly, if you're transporting from one of these to another, there should be some family of curves that's changing. And that family of curves that's changing will, in an appropriate sense, actually give you a character, like a particular of a GM action on a curve. And you can do numerical computations with this character and predict for what values of alpha certain curves should destabilize or become stable. So there's sort of some computations here that you can do. But nonetheless, if you open several of the papers of Albert Fedorchik and Smythe, you can see several of their predictions for what I mean precisely by this. Yeah. And then construct, I guess, a wall crossing. So maybe I shouldn't diagram. I shouldn't fill this in here. I'll move over so everyone can see what I'm writing. And what do I mean by that? Essentially, by your choice of this mg alpha, you're going to be constructing a stack, mg alpha, that includes your conjectured, I guess this is maybe you're expecting this to be some critical value, but it doesn't have to be. Mg bar alpha minus epsilon for some very small epsilon, and mg bar alpha plus epsilon, again, for some small epsilon. So in your construction of a stack, you are saying that when you perturb alpha a little bit, these alpha plus epsilon and alpha minus epsilon stacks live inside it. And then the wall crossing diagram is then to prove the existence of a good moduli space. So all these vertical arrows are good moduli space. Moduli space morphisms to an actual, at least algebraic space, mg bar alpha plus epsilon, mg bar alpha, mg bar alpha minus epsilon. So you're going to construct this stack satisfying some properties and prove that each of these stacks admits a good moduli space and that you have a diagram like so. And then the last part is prove ampleness of k mg bar plus alpha, maybe I'll call it delta. I'm just going to call it delta because I don't have a, or alpha plus epsilon or alpha minus epsilon. Delta is this quote boundary divisor, the image of what the boundary divisor should be on these stacks. And so this is roughly the idea. Once you prove ampleness of this divisor, which is something numeric, then essentially by uniqueness of canonical models, you'll get that this is actually this mg bar alpha for plus or minus epsilon will just be the claimed mg bar alpha. So in some sense, you're approaching the problem of showing this is a moduli space by forcing it to be a moduli space. You're constructing this bigger stack that parameterizes the right curves, and then you are verifying that that stack has the right properties to admit a projective good moduli space, which necessarily is equal to the mg bar alpha you started with. So this is sort of the approach that we are going to take when we talk about this in genus 4. This is maybe not in this level of generality, the original approach with many of the first steps of the Hassett-Keel program, because many of the first steps you can interpret as, I guess, almost a like variation of GIT-like stability. You have some, right, one construction of mg bar. You take the fifth pluricanonical embedding of curves into some projective space, and you do some GIT on this locus. What if you take different pluricanonical embeddings into different spaces? By varying the embedding, you can construct many of these first examples of the wall crossing that's associated and kind of avoid this picture if you don't want to think about this. But this is at least the method of Alper, Fedorchik, and Smythe that we are going to generalize toward. So what happens in genus 4? That's the goal of the talk. I guess we have 20 minutes left. So I can state the theorem, which is we know all the alphas in genus 4, and spend most of my talk telling you how we do that. No, not necessarily. Oh, sorry, under what conditions was your question? Yeah. It really is a matter of how many specializations you have in some sense. So like at least if you want to interpret this in a moduli, I don't know if everyone heard. The question was, are there conditions in which this is an isomorphism on the other side? And sometimes it is. So for example, when alpha is 9/11, it is. So to answer your question in 2 examples, 9/11, 9/11, 9/11 minus epsilon, 9/11 minus epsilon. If you want to do the AFS framework in this case, what's happening is that this stack is parameterizing both what's happening over here, which is the nodal curves, and what's happening over here, which is the cuspidal curves. And this larger stack includes both of them. So it includes this is your genus G minus 1 component. Your genus G minus 1 component attached to a cuspidal curve. You've essentially specialized that genus 1 tail to a cuspidal curve. But the point is, somehow there's only one rational curve with a cusp. There's not moduli of this. So this curve here uniquely specializes to that. So this is an isomorphism in this case. But if you have other cases, you have some kind of you have some positive dimensional fibers over the different points. So this closed point doesn't uniquely specialize to this closed point. Right. Yeah, we typically, like in this case, yeah, there is no morphism from mg bar 7/10 to mg bar 7/10 minus epsilon. Yeah. So this picture is kind of suggestive of what's going to happen. You have something over here where you understand something over here, and the stack in the middle will just be the bigger one that contains them both, morally. So what happens for genus 4? Let's focus in on that. And I hope to maybe also convince you as we're talking about genus 4 that some of these methods we expect to apply in higher genus. So we did this in genus 4 as an application of some of our earlier work, but hopefully there's more to be said. So I guess we'll say this is a theorem. I guess, so this is what we prove. Kenny Asher, myself, Yu-Chen Liu, and Xiaowei Wang. But this builds on all the work that we already said. So all of the steps of the Hassett-Keel program before. So Hassett-Keel, Hyun Lee, and Alper, Fedorchik, and Smythe. So it builds on all of this work. And then there's going to be another necessary input, which will, so this is, I guess, up to, I'll explain what I mean by this in a moment, but then there'll be another necessary input by work of Castellana Martin and Laza and Jensen, which will be essentially alpha less than or equal, well, maybe I'll say less than 5/9 based on what we did. Okay. So we prove the completion of the Hassett-Keel program, but it builds on a lot of other authors. So I'll phrase it like this. The Hassett-Keel program in genus 4 is complete. And let me indicate what I mean by the cryptic notes in the beginning. So what is known by what we've already said, if you start at 1, you have this M4 bar. And we know the first few steps, right? So at 9/11, something happens. At 7/10, something happens. And at 2/3, something happens. So let's say you have some wall crossings, but we'll go ... to I guess it goes this way. M4 bar at 2/3 minus epsilon. So this is all known from the previous works of all of these papers. And then after 2/3, things are a little bit unknown, but earlier work of Castellani, Martin, Laza, and Jensen constructs, maybe before I fill it in, I should say the key input. A genus 4 curve, at least a canonical genus 4 curve, we understand very well. A canonical genus 4 curve is a 2-3 complete intersection in P3. Okay? So I'll put this as a fact here. Let's just say a general genus 4 curve. So here I mean sufficiently general is a 3-3 curve on a quadric surface, a smooth quadric surface, so that 3-3 makes sense. And then canonical is a 2-3 complete intersection. I guess I can write this out. Complete intersection in P3. So the quadric doesn't have to be smooth, right? But the reason for saying that is that in this Hassett-Keel program, at the end, it is known that this Hassett-Keel program terminates with the moduli space of GIT semi-stable 3-3 curves on P1 cross P1. So somewhere at the very end, you have M4 bar. Okay. There's too many numbers. I have to look at 8/17 plus epsilon is GIT of 3-3 curves on P1 cross P1. And then at 8/17, you get a point. So that's where this program terminates. But then the work of Castellani, Martin, Laza, and Jensen was doing VGIT for these 2-3 complete intersections. So you can construct a sequence of moduli spaces, which again are not a priori the moduli spaces in the Hassett-Keel program. Okay? But you can construct a sequence of moduli spaces going up to 5/9 with VGIT. So I'll put it M4 bar 5/9 of 2-3 complete intersection curves. And this is the work. Let me get my CMJL. So they construct a VGIT. It's actually quite non-trivial. So it's really, really beautiful that it works. And you start with a point. I guess you start with the map from GIT to a point, and you change this VGIT parameter, and you construct a bunch of moduli spaces. And then they prove that they are equivalent to the models at the end of the Hassett-Keel program in this case. And in fact, they prove that this M4 bar 5/9, back to maybe the original perspective of looking at Hilbert stability or stability of n canonical curves, this is a Chow moduli space. So this one, I'll call it X, maybe sub Chow. So that's really imprecise, but I mean, if you look at the Chow scheme of cycles associated to these canonical curves in P3, and you construct the natural GIT compactification, the natural GIT quotient, that's what this 5/9 is. Okay. So if you look at it, you're like, oh, look, 2/3, 5/9. This is not a very big window, question mark. So it's almost done. But I think what we did is sort of two kind of fundamentally new ideas to complete this program in this small range. Right? So 2/3 to 5/9, again, not a very big range, but the inputs that we had to do to connect the dots here is two non-trivial things. And that's what I would like to explain in my final 10 minutes of the talk. So let me grab a bigger piece of chalk. The key idea, fortunately in this case, because of the works of AFS getting us to the 2/3 minus epsilon space and CMJL getting us to the 5/9 space, we actually, I'll just draw a very rudimentary picture. M4 bar 2/3 minus epsilon and M4 bar 5/9 know precisely where these two spaces differ. They both have very explicit descriptions. So this has three. I'll draw the image of where they differ. There's 2 points and a curve. So what's going on here? What are these? This is minus, oh, sorry, yes. Okay, first of all, my 3 was an epsilon, so let's try again. 2/3 minus epsilon. Yes. So AFS actually doesn't tell you what the epsilon is. It tells you that at 2/3 there's a wall crossing, and in a sufficiently nearby 2/3 there's a moduli space of prescribed curves. But they don't tell you, maybe we would get very lucky and epsilon is big enough that it takes you all the way to here and there's nothing else. We do not get that lucky, unfortunately. So there's 3 curves in this, or 3 loci that parameterize curves in M4 bar 5/9. And I should be a little bit careful, right? Because this M4 by 5/9 by construction is really a Chow quotient. So it's really actually a moduli space of cycles. But in fact, there is a curve interpretation. So each of these have a meaning. So maybe I'll label them. Get a green chalk. I'll call this, I don't know, just for labeling purposes, 1, 2, and 3. Okay, I'm not going to continue writing in green. Okay, what's 1? The first point, the first I, is the curve, which maybe I'll call C2A5. This is the notation that's used. And what is this curve? It's the unique curve on P1 cross P1, my P1 cross P1, that's 2 fibers, and then a curve that meets the fibers in 2 A5 singularities. So let's see if I can draw. I tried to practice this so I would be able to do it. Okay, so this is C2A5. It's a curve on P1 cross P1 that is 2 fibers and then 1, 3, 1, or 1, 3 curve, however you want to write it. 2, locus 2, so the other curve, I believe the authors call CD. And again, these are 2, 3 complete intersections, right? So it still lies on a quadric. But in this case, it's the quadric P2 union P2. And the curve is 3 lines on each side, meeting the D is for the D4 singularity that appears on each side. So it's something that looks like this. And then I guess maybe I'll squeeze it here so we don't have to move the board yet. The locus 3, this curve, is a one-dimensional family of curves on the singular quadric. And what's maybe important about this, if this is my singular quadric, they're all singular, so they all have some number of singularities, but one of the points is 2 times the twisted cubic. So in this P112, you have the twisted cubic curve, but times 2, 2C. So there's a very explicit description of what all these curves are and how these differ. And our method, essentially, is to, I'll say this in a little bit of an imprecise way, construct a neighborhood of each of these points where you can do the wall crossing and then glue everything together. But we're doing this on the level of stacks and proving good moduli spaces, so we're not really doing a formal gluing in any way. Like there's something going on here. But roughly our idea is to replace each locus separately and then glue the resulting things together. Okay? And there's 2 distinct inputs that we use for this. So by replace here, I mean the diagram is since gone, but construct this wall crossing diagram on the level of stacks and good moduli spaces in a neighborhood of each of the 2 points and the curve. So replace each locus separately and show things can be glued together. And I mean, this makes it maybe sound, you have to show something, but essentially we're just going to define the moduli space for each alpha to be the union of particular open sets. Okay? And how do we do this? So the 2 key ideas. Oops. And they're quite different. So one, so for the curves C2A5 and CD, So in a neighborhood of each of these 2 points, we use, I guess, the theory that we developed with some of our collaborators, boundary polarized Calabi-Yau wall crossing. So we have 5 minutes. OK. So let me say what I mean by this, and then I'll give you the other key idea in just a second. So what is this with, together with Kenny Asher, Dori Baleri, Harold Bloom, myself, Giovanni and Chiostro, Yuchen Liu, and Xiaowei Wang, and then work of Bloom and Liu, we define these objects called boundary polarized Calabi-Yau, which are pairs, maybe I'll say X, C, D, where X is SLC Fano. So the anti-canonical is ample, but X could be SLC. D is ample, and KX, and still X, C, D has good singularities. Can't add any ample divisor. And KX plus CD is trivial, maybe Q linearly equivalent to 0. So we define these pairs, these boundary polarized Calabi-Yaus, and they're interesting because if you have a boundary polarized Calabi-Yau and the ambient space happens to not be SLC, but happens to be KLT, so I know the green's hard to see. So if this is KLT, then if you perturb C a little bit, C plus epsilon D, this becomes a stable pair in the theory developed by Kolar. So Kolar KSBA or KSB stability, this is a stable pair. And if you perturb, so this is maybe the theory of KSBA. If you perturb a little bit the other direction, you get a log Fano pair, which happens to be K semi-stable. And so this framework gives you the wall crossing diagram that we can apply in these cases. So this boundary polarized Calabi-Yau, what we prove, at the very least, I mean, we construct the relevant stacks, and we prove the existence of a good moduli space in several cases. So what we show is you have some stack of the KSBA stable pairs. And OK, maybe also I'm being a little bit sloppy. If X is KLT, in order for this to be stable, you need the log canonical threshold of D to be not equal to C. Right? So there's some other things. But just to give you an idea, there is some subset of these BPCY pairs that are KSBA stable, and there are some subset that are K semi-stable. So this is a moduli space of canonically or log canonically polarized pairs. This is your boundary polarized Calabi-Yaus. This is a moduli space of K semi-stable pairs. And so we construct all of this in these papers, and then in relative dimension 2, in dimension 2, we prove that. OK, well, maybe before I ignore that at the moment. What is already known is that this admits a coarse moduli space, MKSBA. This admits a good moduli space of the polystable pairs. And what we prove, and then it's generalized by, we prove in the P2 case, and then Harold and Yuchen prove it in more generality. If the dimension of X is 2, there's a pair, there exists some sort of moduli space. I'll put it in quotes. We define, it's technically not a good moduli space, but it's close. There exists a good moduli space here. But this is roughly the diagram we wanted, right? In order to construct these moduli spaces of the Hassett-Keel program, we wanted this diagram. The difficulty here is that all the moduli spaces constructed in this setting are moduli spaces of pairs. So for, we'll say, pairs X, C, D, I'm almost out of time, so I won't tell it. You can ask me more if you want. In a neighborhood of these, either D equals C2A5 or CD, you have a forgetful map. Maybe forget. From the space of pairs to just the divisor. And we prove that in this neighborhood, this is in fact an isomorphism. This is false for the other locus, for locus 3. Okay, so we fundamentally cannot use this method for the third locus. But essentially, we get the wall crossing we construct we want in the Hassett-Keel program just by doing it all on the level of these pairs. And you get some really interesting geometry. Like we can say precisely what the kind of corresponding locus in here is above each of these points. But then, since I'm just about out of time, I don't have time to tell you too much about the last case here. But I guess, this does not work for locus 3. And there's something interesting here, in fact, that the people who are familiar with the Hassett-Keel program, locus 3 contains the point that is the doubled twisted cubic, which is a ribbon. And so the people who've done this before, this is supposed to be kind of the image of the hyperelliptic curves. At some point, the hyperelliptic curves are going to get contracted in the Hassett-Keel program, and their images will just be taking the canonical map and giving you this ribbon. So this locus, you have to do something different. And maybe just in words, I will say we define maybe okay, in the paper we call it this, but a stackification of the Chow quotient. And use it to replace the, I guess ribbons and other curves in this locus 3. So what do I mean by this? Just maybe I'll say in words. This M4 by 5/9 is this Chow quotient. It's a moduli space of cycles. So what we construct is a moduli space of curves, actual curves, that admits the Chow scheme this GIT Chow quotient as its good moduli space. So it's strictly, it has more curves than, the map. The Hilbert-Chow morphism is not an isomorphism. There's more going on here. But we construct a stack of curves that admits this as its good moduli space, and so show that there's maybe some VGIT on this stack of curves that allows you to go on one side, get the 2/3 minus epsilon moduli space, and on the other side, this 5/9 moduli space. And we expect this to work for hyperelliptic curves and possibly other k-gonal curves where k is not the generic gonality and some amount of generality. So this is kind of very similar in spirit to certain moduli of branch varieties. But I won't say too much about this other than this is the part that we expect to generalize to beyond the case of genus 4. So I'll stop here. Thank you very much for your attention.